Again, thank you very much. This talk is an introduction to AutoML. It's a really interesting area of both research and production work these days. And I want to go through a lot of the concepts, sort of a survey of that, but then also dig into examples of, what are the different areas in AutoML? What are the open source projects that are available? And really take a look at some of the more long-term trends of where this is leading to. By the way, this talk came out of collaboration. I was working with Tim Bonneman, and also I'd co-authored an article with William Roberts at IBM Data Science Community. And previously, I'd done a report about open source for AutoML. Ben Lorica, who was formerly at O'Reilly Media and had been the chair of or co-chair of the AI conference and Strata Data conference, Ben had originally asked me to do a industry survey of what was going on. And so this talk really follows up from that. We want to give you some hands-on, show you some code, and I hope that this is a nice introduction to the May 28th workshop coming up on AutoML. So if I wanted to try to present AutoML with just like a one-liner statement, the idea is it's really about gradients. And so let's talk about how we work with differentiable data and gradients, and what the relationship there is with machine learning and AI. If you look inside of a typical supervised learning, machine learning algorithm, there's a few main concepts there. There's the notion of having different learners that are trained from data. Typically, the algorithm can be expressed in terms of a loss function and a regularization term. Typically, there's some use of approaches such as stochastic gradient descent that are being used to train the learners. Now, if we clear some of this out. If we were to go through and look at a particular algorithm, for instance, here, let's say we use the iris data set, which has 3 species of iris flowers, Setosa, Brassicella, virginica. It's very well known, very well studied. It's great for clustering. There's one label, and then there's 4 other independent variable columns that provide the features. If you were to go in, for instance, and use random forest, which is a very well-known algorithm, to try to illustrate what's going on inside there, the learners are going to be individual decision trees. We can talk about the loss function that's involved, looking at information gain, and so rough equation for it there. We can talk about the regularization term in terms of how do you prevent overfitting, really. How do you try to have something that's generalizing from the data? And we can also discuss, the use of essentially a gradient that we're following as we train and add more trees to construct the ensembles of a random forest. I've got examples of this in a notebook that's associated, we'll go through at the end, but showing the iris data set. Now, I also need to distinguish a couple of things. Once you train a model, once you've trained learners, there are going to be parameters that represent what those learners are. Those represent the model. Those can be serialized, so you can go out and deploy the model later. And so these parameters are basically how it's learned to differentiate different classes of data within, again, this kind of multidimensional gradient. And the parameters can be very large. When we talk about deep learning and transformers like BERT and the other Sesame Street characters that are being used in natural language deep learning these days, some of those models have billions of parameters. But there's another notion of something called a hyperparameter. And the idea there is, what are you providing to help guide the machine learning algorithm so that it can try to search for optimal parameters? So for instance, if you were doing random forest, you might specify a hyperparameter for the number of trees. If you're doing some sort of clustering, say k-means would have a hyperparameter of k, number of clusters. Of course, k-means is not supervised, but you get the point that you're using hyperparameters to guide your search toward optimizing the parameters, optimizing the learners in the model. Um, so for instance, with Iris, using random forest, we can go back in and say, well, if we've got a hyperparameter of n trees, say we choose 10 to be the limit of the number of trees to train, then we're going to have 10 trees times the number of nodes in each of those decision trees based on the number of dimensions. So we can specify some bounds on each of those. Now, generalizing from this, if we take a look at gradients, supervised learning, typically we have a training set. It has labels. It has independent variables used to predict those labels, and we differentiate to find out, how to optimize the learners to produce that. In unsupervised learning, it's a lot of the same thing. It's just you don't have the labels, you don't have the classes, and instead you're going to be looking for a signal within the noise, looking for a structure within the data to be able to produce some form of classes or structure that are emergent, and then possibly go in and explore them and add labels to them. This is what clustering is, typical thing. We can also talk about active learning, which you may hear as human in the loop. For one of the definitions of active learning is that it's much like supervised learning. It's just that you look at the uncertainty of what's being predicted from the model, and if the uncertainty passes a certain threshold, then you can kick out the judgment, the decision, to a human who has domain expertise, and they make a decision, and then that data point goes back in to help train the model. So it's kind of a feedback loop, iterating. There's also self-supervision. Facebook and others have produced some very large-scale case studies about this. And the idea there is if you can take an object and take different data about it, look at different views of data from the same object, then you can start to use them against each other. In which case you're also constructing kind of a gradient. You're reapplying a lot of supervised learning techniques. Of course, we talk a lot about deep learning, many layers of neural networks. Obviously there's some connection between them, structural features such as autoencoders and others that work in between the layers. But it is supervised learning. Reinforcement learning introduces something very different, where we have one or more agents that are within an environment, possibly a simulated environment. They have this exploration, exploitation trade-off that effectively constructs a gradient, and then from there, it is a kind of supervised learning, if you will, to develop policies. And they may or may not have models, which is one of the interesting things about reinforcement learning. We can go into that in another time. There's also a notion of something called weak supervision, where you can take relatively noisy input from different subject matter experts and then model the input from each subject matter expert with label functions. So you're basically constructing a gradient about the human decisions that go into preparing data, even before you use it to train. And then you can propagate that through and get some feedback in terms of how those judgments bear out in practice, how you can go and adjust those functions later on to improve your training data. On and on. But I want to just really reinforce this part that we really make a lot of use out of finding structure in data by doing some sort of optimization on gradients. Oh, and one last point, meta learning. And this is where you can leverage information about the data preparation, about the configuration, about the hyperparameters, and all this that go into, you can think of like an end-to-end lifecycle for machine learning. For building these ML workflows, can we capture that over time and effectively build up a knowledge base of what kind of work has gone into training machine learning models? How well has it worked? And therefore, when new people come up with similar kinds of scenarios, can we pre-populate their configuration? Can we suggest to them approaches to use based on previous learnings, et cetera? Meta learning is a very large umbrella of research. It's very active, very exciting to see this. And also some examples of that today. Okay, so the idea is that we've talked a lot about search. We've talked a lot about trying to find the optimal hyperparameters to be able to optimize learners in a gradient. So in some ways, a lot of these machine learning problems can be described as search. And I'm getting rather gray now, but if you were to go back to the time when I was a grad student at Stanford in computer science, talking with the people in hard AI back then, much of their emphasis was on search. And you know, they talked about A star and B star and generalizing problems in AI that were formulated as search problems. Probably no small coincidence that one of the major outcomes of that program was a very large search engine, actually two of them. Okay, so if we talk about formulating a machine learning problem in search, how can we find the best hyperparameters for a given use case and given set of input data? It's not simple. It's not magic. This requires a lot of computation. We'll go through that. But essentially, we're leveraging machine learning to help make machine learning more effective. Now, there's a lot of issues here. It's not a simple kind of optimization. You know, for instance, we have to include not just optimizing for loss, but we might want to take into account things like, you know, other types of trade-offs. How do we deploy the model? Does it fit well with the use case? Is it too large for an embedded use case, for instance? Does it require safety requirements for the production environment in terms of security? How about fairness and bias? And how about other types of trade-offs that have to be taken into account? And frankly, there's a lot of human decisions that go into the mix for machine learning workflows. So again, I want to impress that this is not a simple thing. But we're starting to see some ways to leverage machine learning for most all of these points. Now, consider if you had a data set and you had a use case and you're trying to look at all the possible variations to be able to optimize to produce different machine learning models. That's a very large potential search space. But if you start to have some perspectives and learnings from prior work that you can accumulate and apply, well, that's like using heuristics in search. That's like optimizing in search. And so the goals of AutoML can be stated as a search problem. You're looking for appropriate hyperparameters. You're trying to identify features and data transformations to get to the right training sets, even before the point of using hyperparameters. You're also learning from history overall. And that's kind of, in my perspective, a lot of how this field is rolled out, because the original work was very much focused on hyperparameter optimization, but later on it's began to expand out into a larger and larger account of the workflow preparation, and therefore you get into more of this meta learning kind of use cases. And I also want to impress that machine learning, of course, has become very popular. It's hilarious. I was going out and teaching an industry. You know, if I look back at like 2014, it was something you had to convince people about, that machine learning had value. 6 years later, of course, that's ridiculous. People recognize the value. So it's grown, but the use cases have grown too. There's a couple of great papers that I'll point to about some other long-term considerations. One is show your work, where, you know, we've got to this point of very large models. In some case, there are diminishing returns on some of the models. They may have higher and higher predictive power, but there's diminishing returns. And in some cases, you know, there's a trade-off between getting just the absolute best predictive power versus time to market for a solution. In some cases, simpler modeling may be indicated. And so there's a great paper showing those trade-offs and how those can be leveraged. Another great paper called Energy Policy Considerations for Deep Learning in NLP, which talks about the carbon footprint and just, you know, the fact that training a transformer with NAS, neural architecture search, you know, in some cases you're looking at a carbon footprint to train one model that's equivalent to running automobiles, 5 automobiles for their entire lifetime, gasoline automobiles. So there's a lot of considerations about energy, policy, cost, outcomes, etc. Fairness is also another big issue that we're looking at, and we'll show some examples here. There's a great paper from Stanford about why it's mathematically very difficult, if not impossible, to design fair machine learning models. You really have to accept trade-offs and own them. And there's other work here talking about how to detect biased data sets, how to remove that, etc. I'll point to one of my colleagues, Trisha Mahoney, did some excellent tutorials about the AIF 360 models in OSCON last year. And one of the consideration is that while we talk about optimizing machine learning models, what does optimization mean? If I were to talk about accuracy of prediction, even accuracy itself can be described in several ways: precision, recall, specificity, perplexity, et cetera, et cetera. We may optimize in terms of how much does it cost to compute the training, or how long does it take to compute the cost of training given the hardware available. How scalable will the end result be, the models when they're deployed? Are there attack surfaces being exposed? Does it satisfy needs for compliance, explainability, et cetera? Okay, so those are a lot of the considerations, but now let's take a look at where some of the solutions are addressing those issues. And first off, just to try to provide a landscape for the kinds of solutions that are emerging, let's talk about the end-to-end machine learning lifecycle, because AutoML tends to address different parts of this, in some cases almost all of it. And I'll point to a set of articles and YouTube videos. It was from a track that we did last summer at OSCON called MLOps Day, really bringing together a number of different enterprise companies and talking about their practices for managing ML lifecycle. If I were to try to provide an idealized view of this, typically you've got some sort of data preparation that leads into some feature engineering, which is a hard problem. You train models, which is what everybody talks about, but really that's only a small part of the thing. You spend a lot of time evaluating the results because different algorithms really have, it's not an apples to apples comparison of how you evaluate the results and how you select models as a result. And then there's deployment issues in terms of auto scaling or distillation, a lot of this. And what I want to impress here is that at each step in this workflow, there are also on the top line, different areas of AutoML that are emerging. So for data preparation, there are forms of auto data prep. For feature engineering, there are areas of feature selection to have more stable solutions, for instance. Obviously, training models, there's hyperparameters, optimizing those. But then in terms of evaluating results, there's a notion of automating or semi-automating model selection, building ensembles, et cetera. And then when it comes to deployment, there's other AutoML features there. There's been a lot of work in data governance over the past 2 years. 2018 was really a banner year showing the need for data governance and a rise in that. There's also been, as I mentioned, a lot of rise over a similar period in terms of ML ops practices. What's interesting is when you look at this kind of triangle of data governance, ML ops, and AutoML, they feed into each other. Data governance leads into platforms and practices that guide your operations. Your operations tends to collect the data that's needed for effective AutoML. And then AutoML provides affordances that feed back into, again, needs for data governance. So it's really interesting to see this kind of virtuous cycle emerging between these three areas, which again, over the past couple of years have really been exploding. Here I've got a spreadsheet that's open to the public. I've been curating it in terms of different projects that show up, and I'm only able to show a little bit in the view here, but there's a lot of different open source projects. We'll take a look at a few of those. One of the resources that I highly recommend, this is on GitHub. It's called Awesome AutoML Papers, and it's updated about once a week. But it's really great because it's got this taxonomy of the different areas of AutoML, and then it's got examples from each. What are the latest papers? I highly recommend that as a go-to source for checking out what's going on in this area. Okay, let me break it down real quick in terms of the different areas. In terms of preparing your data, we talk about how data science teams spend 80% of their time cleaning data, and that makes sense. If you were a hedge fund manager on Wall Street, you would spend probably 80% of your time curating your portfolio. And so in a sense, that's a lot of what goes on in machine learning, is you really require so much out of the data. It is the valuable asset. Now, there are ways that we can leverage AutoML for this. And a couple of examples, definitely I would point to what's going on with Snorkel and weak supervision. Also really interesting, based off of ideas from Snorkel, is HoloClean. And I got to talk with the author a few months back about that. These are increasingly being called auto data preparation, ways that we can automate or semi-automate different parts of putting your data together. And the reason being that when you go through the workflow, if you get in trouble when you're training models or get in trouble when you're doing evaluation, you can go all the way back to the data preparation stage, change some parameters, incorporate new data, rinse, lather, repeat, run the whole thing again. So that's a benefit, especially on the ops side. Feature engineering is a hard problem. Deep learning has made great inroads on that, but it isn't a solved problem. I will definitely point toward an excellent book by a couple of friends and colleagues, Alice Zhang and Amanda Kasari, Feature Engineering for Machine Learning, which came out a couple of years ago. And there are some great areas where AutoML can come in here. MLBox and AutoML Toolkit are a couple that really try to approach this. I would definitely point you toward this paper on the stability of feature selection algorithms. A friend of mine from U Manchester is one of the main authors on that. I got some time to talk last year about it. Really interesting work on how can we have stable sets of features over time that lead to more stable machine learning workflows, and some of the issues there are non-intuitive. A lot of people, when I first started looking into AutoML, when I talked to people, a lot had the opinion that all it was hyperparameter optimization. And maybe years ago that may have been true at first. It's definitely not the case now. But this is sort of the core of what's been going on over time. And when you look at some of the projects, there are some that are just foundational. Definitely check out HyperOpt. It's been used by a lot of other projects. It's part of, again, this kind of foundational building block for hyperparameter optimization. And again, this just strikes the core of using gradients at a meta level. There's also RayTune. I do some work with the Ray project. There's AutoKeras and others. Great article about this general area here from it's called Stop Doing Iterative Model Development. Highly recommend that. Then once you have different algorithms applied, different models produced, you want to evaluate and sort of do a bake-off between them. How do you determine which algorithms best fit the use case? How do you compare different models? It's not simple, and in many cases, it may turn out that using ensembles is, of course, much more powerful. I point toward Introduction to Ensemble Learning. There's great material that came out of the Netflix Prize regarding this, of course, years ago. AutoSKLearn, AutoScikit-learn is one of the kinds of tools that can leverage AutoML at this point. And then once we get down to deployment, there are a lot of issues. And certainly we've seen this coming out of things like SageMaker, of course, Watson Studio, Knative, et cetera. One of the really interesting areas of this that I would definitely point you toward is the TinyML movement. And so definitely check out TensorFlow.js. Certainly TinyML Summit is one to watch. Really fantastic work of being able to put deep learning trained at cluster size and fit it into very small chips that run off of, like ambient light kinds of energy levels, 256K kinds of memory spaces running on bare metal, but still being able to do computer vision and voice translation. Okay. So, those are some different areas of AutoML, and I'm going to put in a slide here from my colleagues at IBM in terms of some of what they're doing in Watson Studio, comparison of AutoML and AutoAI, and I can point you toward more forums that will give much more information about this. Looking ahead, I want to point toward again, this concept of meta learning, somewhat of an umbrella, but it really does encompass the entire end-to-end workflow. And how can we leverage what we learn over time, especially within the context of teams and organizations. And this dovetails with notions of knowledge graph, if you will. There's some great papers that describe this, definitely the SmartML paper, model agnostic meta learning, learning the Malik paper from Learning to Optimize, etc. And we'll look at an example from Lale. There's also Teapot, which do some interesting meta learning. Another thing that is really fascinating is to see where machine learning helps automate the process of creating software, including creating machine learning applications. For one example, I would definitely cite looking at AutoPandas, where you can take input data and data frame, and then you can specify a goal of how you want to reshape that data for a use case, and then it will automatically generate the code to get there. Definitely check out AutoPandas. Another one that's really great is AI augmented autocompletion. If you haven't seen that from tab 9, that's really fantastic, using deep learning to do really, really smart autocompletion. And there are other examples of this as well. But this is an area of program synthesis that's not exactly AutoML, but it definitely dovetails. And really, for looking much further out, there's an interesting video from TensorFlow Dev Summit, interesting video by Jeff Dean from Google, talking about the trade-off of being able to hire enough people with expertise in machine learning versus not, and how we can replace people at a cost of approximately currently about 100x increase in cloud budget to offset the difficulty of not having enough AI experts. And basically, AutoML is a way to address that in industry. It's somewhat controversial, but it does underscore a lot of the trends that are going on currently. Okay, so definitely stay tuned. There's a lot going on in this area, and effectively, this is a way of getting machine learning models to be more clever and help AI to improve AI. So that's a lot of the promise of what's going on in AutoML. And at this point, I'm going to cut over and show a few examples, and then we'll go to the more Q&A and discussion. So let me get back to here. I mentioned earlier about an iris data set, exploring it and showing sort of a peek inside of a machine learning algorithm, how it's operating. And so if you want to look at that, there's just some very simple examples here. But what I'd love to show would be, there we go. Let me load this up. I have some Jupyter notebooks which show examples. And I have here some examples from Ray using RayTune, and then also from Lale doing more of the meta learning, the whole encompassing thing. And these are available on GitHub. We'll post these later on along with the video, etc. But here's an example of using the Ray project. And like I say, I'm also involved in that. I'm helping build the RLlib tutorials for Ray Summit. And here we bring in Ray, which is for augmenting machine learning in Python. And what we're going to do is, let me scroll down here. Basically, this part here starts Ray up at the top, and then down here we're providing some parameters. What I'm going to do is take this function, easy objective, which is a kind of trivial function, but effectively it's a loss function with a regularization term. So it's sort of this like abstract machine learning model. And we're going to run over some iterations. We put in a sleep just to give it a cost. And so if we consider that to be a bare bones algorithm, here's a way of using Ray to apply a way of doing AutoML for hyperparameter optimization on that. And we'll give us some parameters here. I'll go through 10 iterations. Each episode will have 100 time steps. But then it's pretty simple here. We have hyperband scheduler, and we run RayTune. And you can see, I'll scroll through as it goes through, but if you look at the algorithm that's being optimized, you can see that the loss function there, it's the height minus 14 squared. So you can imagine that the height parameter is going to zero into approximately -14 pretty quickly. And that's in fact what happens. I'll let you run through, but it goes through training. Of course, Ray is used a lot with reinforcement learning, which has a lot of overlap here with what's going on in hyperparameter optimization. The two fit pretty well together. But let me scroll down to the bottom. Yeah, and there you see those parameters start showing up. The height shows up at approximately 14. So it zeroes in after time. And I'll show one other example that I really like. Here, let me, Jupyter Lab. And as Bill mentioned, I'm one of the co-chairs for JupyterCon. We'll be doing our virtual conference later this year. Highly recommended if you're interested in Jupyter. A lot of really interesting machine learning work going on there. I'm going to go into a project called Lale, which, let's see here. Let me get this. There we go. So for instance, I can show cross-validation. I can show there and top K. Okay. So Lale provides a high level abstraction that incorporates a lot of other really interesting components of AutoML. And so to a large extent, it is implementing a lot of ideas from meta learning. In particular, it provides a kind of grammar for the different stages of a workflow and how to find optimized components for each stage. So you can see down here where really this is training PCA toward a logistic regression model, pretty standard, straightforward stuff. It computes cross-validation to be able to show, what is most optimal. But it really encapsulates that idea of having an entire workflow. And then here is an instance of using Lale working with a class imbalance. So again, getting back to notions of fairness and bias, trying to understand what's going on with a particular training set that has some bias that's observable, and how can we go back and try to work with that. Similarly, I would point toward, here's a demo for the AIF 360 project, which is also an umbrella of several different algorithms from IBM, Google, et cetera, for trying to detect and correct for imbalance and other areas of fairness and bias. But here's an example of using Lale with AIF 360. Really fascinating work. Again, a lot of this is very difficult. It's computationally complex, but it's super valuable looking at the whole end-to-end pipeline. Alrighty, let me jump into Q&A because I know we've got a lot of that. So I'm gonna stop sharing and I'm gonna jump back over to the Q&A side. And, oh, okay, great. Could you please help us with the GitHub link? Yes, I will. And actually, while I'm answering questions, if my colleague Tim is on the line, he can also point you toward, and I'll get the GitHub repo in there. Oh, great. Okay, somebody posted in. Thank you, David. You posted in the link to Awesome AutoML. By the way, I should mention that the slides that I have a lot of links in them, and I try to err on the side of actually having way too many links. So when you get the slides, all the links that I've mentioned are going to be in there. And let me look through other questions. Oh, great. Thank you kindly. Khalida, thank you. Great. Thank you, David. Thanks for posting in those. Okay, great. Perry has a question. What is the difference between AutoML, MLOps, and ML pipeline? Okay, great question. So to try to address that, let's take the most fundamental part of that would be an ML pipeline. So again, let's take this kind of idealized notion of stages that we go through when we're working with machine learning. Typically, there's a lot of work that goes into data preparation. And a lot of that may be a matter of discovery, exploring what is in the data, what appears to be useful as far as predictive features in the data. So the data prep, we talk about that being 80% of what we do on data science teams. And there's a lot of truth to that. And so that's one stage of the pipeline. And then the results of that feed into the next stage. Typically, let's work toward having the best set of features we can to provide as training sets to train machine learning models. And that's a hard problem for a lot of reasons. A lot of it is very counterintuitive. You may be working in very high dimensional space. And it's also just a very, very hard problem when you get into the kind of statistics that are required for a lot of those decisions. It's oftentimes beyond the scope of what many people working in data science really have even been exposed to before. So I definitely recommend checking out Alice Zheng and Amanda Kasari, their book, excellent book, Feature Engineering for Machine Learning. It will give you some taste of just how deep down the rabbit hole you can go in feature engineering. And then later on, you train models and you go in and you evaluate the results and try to figure out what's good. Do you want to put different models together into an ensemble, et cetera? And then later on, you have to deploy the models and then manage them in production. So that's the notion of a pipeline. All those stages concatenated together and the feedback loops in between them as you discover better ways to revise your pipeline. Once you've got that pipeline in place and the team is working on that, and you produce models and you have ways of updating them, Then when you get those models out into production, in deployment, one of the first things you'll find is that models degrade. And so you may have the best training set available, but once you deploy a model and it's interacting with customers in a live environment, the environment's going to change. And so the data is going to change. And so the model is typically going to drift. So there's a lot of need to update models and monitor model drift and monitor possible security issues. Like if you're doing an anti-fraud model, are the people who would do credit card fraud, are they actively attacking your anti-fraud measures, attacking your models? Because there will be an attack surface probably exposed in some way. Those are operational issues. Again, I would point you back toward there's some really excellent presentations from that MLOps Day set of presentations. Really great stuff, especially Donald Miner's piece about really what are the criteria for MLOps? What are we trying to solve for? What are the gotchas you need to look at if you're just coming into this and you don't understand the typical kinds of failure modes? Okay, so once we build up pipelines and then we have operations on top of them, AutoML is a way of leveraging a lot of the data that you collect out of ML operations. The data that you collect when you're preparing your data, that can feed into auto data prep. The data that you collect when you're training models, that can feed into guidance on how you do hyperparameter optimization, at least where to start, on and on. And so that's kind of the thesis of meta learning is how can we collect a lot of that data and then apply it later on. And again, the other part of this is data governance. The needs for data governance were very much accentuated in 2018 with a lot of breaches and Cambridge Analytica on Facebook and other things like that. And so now, I've been around in the industry for almost 40 years, and we didn't really take data governance seriously enough. We kind of swept it under the rug a lot. But since 2018, of course, GDPR and other factors, it's extremely serious. And it's nice how data governance, MLOps, and AutoML feed into each other. Okay, David, with AutoML, data scientists and engineer engineer jobs are not going away. In fact, a lot of the emphasis that I see currently on AutoML is just because it's so hard to hire enough people with the skills in machine learning and data science. So in a way, this is a way to augment that. Basically, can we burn a lot more cloud computing and try to augment people who are on these teams? But again, getting it 100% right is just not something that machines are going to do yet. That's a long ways off. So I'd say that if you're interested in this field, if you're working in this field, you're in a really good place. And seriously, you look at even in the current economic crisis, a lot of the AI organizations are doing very well and even hiring more. Yeah, AutoML is something to have in your toolkit and leverage as much as possible, help make your teams more effective. And obviously more return on investment for your data science teams and for your AI deployments. Therefore, it's a lot more justification to have more. Gina, great question. What are some super basic intro links for people who are trying to handle a lot of data on a team, but we're new in machine learning? Yeah, that's great. Great question. If there's a lot of data, how do you get in and start doing some discovery, start to really understand that? There are very sophisticated techniques here. I definitely think that HoloClean is probably one of the most promising projects. Ilya out of Waterloo, of course, is the leaders on that. And there's also work at Stanford and Washington, et cetera, where Snorkel came out of. There's really sophisticated work on that. But what you're asking really speaks to the core of a lot of data science work. So how can you handle a lot of data, but you're new in machine learning? Really dive in. I give a suggestion that if you want to brush up and work with experts and learn a lot of techniques quickly, I would definitely recommend organizations like DataKind, which is a place where data scientists will volunteer on teams and work on projects for nonprofits for social good. It's a great way to build a portfolio. It's also a great way to really rub shoulders with people who are expert in this field and work with them directly on projects and learn a lot of techniques in other areas that you can take back into the workplace and apply in your projects. There's a lot of great tutorials about this, definitely. And I hope that some of the links in the slides will give more indications about that. Certainly the awesome AutoML papers has a lot of links in different areas. And data preparation, of course, is the name of the game there. If I'm sure, There was an example, the random forest model with n trees in the average data set. Do we need to set n to be an odd number? Oh, interesting. You know, there's a wide body of research going back to 2001 when Leo Bremen and when Bremen and Carson published that paper about embedding and boosted aggregation. I'm not going to dig into a lot of details on random forest. And in some ways, I mean, I've used random forest a lot in my career over the past 20 years. But there may be actually better ways to handle things these days in some cases. Um, yeah, I just picked the number 10 because it was going to show a pretty interesting gradient if we only went out that far. Um, there's a lot of other good papers about how to select the number of trees appropriately, and some of these tools will do that. I think that that's actually part of auto scikit-learn. Okay, what are, Kaniska has a question. What are some of the simple business use cases where AutoML can be applied as a black box by a business executive without worrying about tuning the model? That's an interesting question. There are definitely cases where we're seeing this, and we're definitely seeing companies that are approaching that. If you look at the spreadsheet, I had shown the spreadsheet with a tab open to open source projects. The other tab is about commercial vendors. And you look at a lot of them. Basically, all of the cloud vendors have some sort of service along these lines. And there's other companies like Datadog and others that are really focusing on this. And I think across the board, they're doing brilliant work. Google, of course, really put that commercial use of the term AutoML out there pretty early. IBM has AutoAI and Google, Amazon, Microsoft, etc. They all have these. Can a business executive pick it up and use it automagically as a black box? Yeah, there's problems with that. I mean, that opens up issues of like attack surface and fairness and bias and ethical issues. So I do worry about that. I think that what we will see sooner than later is a lot of these kind of services being injected into, for instance, where do you have data frames? Well, a spreadsheet is effectively a data frame, very close to it. Of course, it has a lot more kinds of functions, but the data representation is a kind of frame. So I think we'll probably see a lot smarter services being injected into places like spreadsheets online from cloud providers, or like in Jupyter Notebooks where you've got data frames from pandas. We'll see more and more of these kinds of techniques being used. But I'm always cautious whenever I do a lot of presentations. In fact, this presentation started out for the executive summit at the AI conference. And now it's morphed into more of a developer presentation. I'm always leery about the notion of automating too much just for a business executive. It's important to have the domain expertise, but also there's a lot of gotchas. And AutoML is not magic. It does require a lot of compute time. The examples that I've shown actually take a while to compute, and they're fairly simple examples. When we get into much more extensive examples, we can talk about running clusters for weeks at a time. So I hope that answers some. Let's see, other questions over on the other side. With many vendors offering AutoML solutions, are there comparisons to those in terms of model performance and accuracy? That's a really good question. I mean, that would be a later study. This one here really started out as a survey of what is available and really understanding the terms and some of the trends. Doing a bake-off between the different services. It's been fairly early, but I think we're approaching a horizon when that kind of comparison among services, I could see a McKinsey or a Deloitte or whatever doing that kind of thing, and maybe in some subsequent version. I think we're almost on the point of being able to do some analysis of that. Definitely, I would point toward one of my colleagues, again, I mentioned this originally came out of a collaboration between myself and Ben Lorica. Ben Lorica is no longer at O'Reilly Media. He's now leading a company called Gradient Flow, and they do some comparisons like that. It's a really great podcast series. I'll point you toward that over there. We're also covering some of these topics on the IBM Developer Podcast. And again, my colleagues, Tricia Mahoney and William Roberts, are doing a lot of great work over there talking with experts. IBM PSS modeler has auto modeling and auto data prep for, yeah, good. Uh, yeah, there's a lot of sophistication. And you know, okay, so this is a really good point, that there's been a lot of crossover. If you go to my homepage, by the way, which is, let me type in here. Okay, if you go to my homepage and you look at my videos, I've got a YouTube channel where I collect video interviews and talks and whatnot. And there's a gentleman from France who's an IBM Grandmaster on Kaggle competitions, and we had a great conversation. It was really a couple of years ago, if not 3 years ago, and we were talking about how there's been this crossover. Both of us have a background in optimization, but also a background in machine learning. Effectively, machine learning is a subset of mathematical optimization. That's very clear. But there's been a lot going on, you know, since the 30s and 40s for large industrial or government use cases for optimization. Um, it's interesting to see these tools. SPSS is a great example of doing simulations and optimization. And it has some modeling and data prep, but that's not exactly the same as what we're saying when we look at doing feature engineering that's going to feed into deep learning. Those are not exactly apples to apples comparisons, but it's very similar ideas. And there's been a lot of crossover between the optimization world and machine learning world. And we see great applications in industry for that. I think looking ahead, there's a lot of crossover between what's going on with AutoML and what's going on in general in the reinforcement learning community. And you know, a point that I'll make there is that in reinforcement learning, if you pick up any of the environments that are used, whether you're talking about RLlib or OpenAI, GEM, or whatever, they tend to use these environments that simulate some sort of mechanism, some sort of physics, some sort of game mechanic. And then they run optimizations over time on those. What's interesting is you'll find companies like Pathmind, for instance, which leverages industrial optimization at scale. Whether you're talking about, you know, SPSS or CFlex or any of those, but in a lot of different areas where we're talking about supply chain and factory management, areas in electronics and manufacturing, a lot of really interesting work that goes back decades in terms of simulation and optimizers, solvers, and simulations. And now that has really interesting crossover because that can bolt into reinforcement learning and apply effectively deep learning to develop policies over time for very robust kinds of responses to typical considerations that come up out of those optimizers. So definitely look toward that. It's not exactly AutoML, but it's pretty close. And I think we'll see more and more convergence over time. Mir asks, are there good AutoML online courses and books I can recommend for experienced data science people? You got me there. I haven't seen a whole lot yet. And frankly, the reason why this talk started was, like I say, my colleague Ben Lorca was co-chair for the AI conference, and we weren't seeing enough of the vendors step up and give talks about AutoML. So our thinking was, let's do a survey and see if we can beat the bushes and get the different vendors or different authors to say, wait a minute, why are you talking? I should be talking instead. And in fact, that's what happened. You know, I got up there and presented to a business audience and had a bunch of people afterwards going, no, I want to do that talk instead. So we're hoping that we're going to see more toward this, particularly on the author side. Certainly there's a lot of great papers. As far as having a really canonical textbook for this yet, I think it's pretty early. There's a lot of great survey papers that are coming out. You know, again, if I were to point to any one source that's kind of like a textbook, it's that awesome AutoML's paper site on GitHub. So there's kind of an interactive textbook, if you will. But I haven't seen a lot else. Certainly there's been a lot published, especially when you look in terms of, you know, ensembles and feature engineering and hyperparameter optimization in the individual areas. And I've tried to point out to a few of those. Great, thanks for pointing toward the MLOps state. Great. Straight jacket hanging on the wall. That's not a straight jacket. That's actually a chef's jacket, but it does look a little bit like a straight jacket. Let me see. I can't even see it in the back here. Yeah, no, it does look like a straight jacket. And also, I'm in the top floor above what used to be a bowling alley, and that literally is the concrete walls and ceiling with the raw installation up there. It really does look like a padded cell, which is probably appropriate. Years ago, I was accidentally called an evil mad scientist in front of a lot of people by one of my colleagues, DJ Patil, and the moniker stuck. So yeah, I think the straitjacket's probably apropos. I know we're coming up on time. I want to thank you all for excellent Q&A.